radicals are very high energy and very short-lived. So anything that we can do to stabilize them whatsoever will have a really big effect in their likelihood to be formed. So what that means is that we have to figure out what is the trend of stability for radicals, okay? And I just want to show you guys right now. Basically, this is the trend. And what you're going to notice is that I'm going to compare this trend to the trend for carbocations. Now, if you don't know the trend for carbocations yet, that's okay. I'm just going to point out the major differences here, okay? So first of all, radicals are electron deficient. Now, what I mean by that is that there's an orbital, right? And usually each orbital has space for how many electrons? 2, okay? That's the Pauli exclusion principle. But in this case, we have a radical with just 1 electron. So that would be what we call an partially filled orbital. That's not very stable, okay? So any way that we can push electrons into that orbital, that will make it more stable. And there is an effect that does that, and that effect is called hyperconjugation. Okay? What hyperconjugation says is that the more R groups you have around an empty orbital or a partially filled orbital, the more stable it will be. Okay? So in this case, what I want to do is I want to basically say, okay, the more R groups are on my radical, the more stable it's going to be. Easy. And notice that that trend does hold true. This actually holds true for both carbocations, which are empty orbitals completely. There's nothing in there. Okay? And radicals. They're really the same thing. So notice that for my increasing stability, I have here that I have a tertiary here. A tertiary carbocation is very stable. And I also have a tertiary radical kind of at the top here. Okay? But notice there's a slight difference here. It turns out that tertiary is the best type of carbocation that I can form. Okay? But it's not the best type of radical. I actually have a different type of radical here that's more stable. And that's because it turns out that unlike carbocations, allylic and benzylic radicals are actually going to be the most stable. Now, allylic and benzylic are just words to mean that you're next to a double bond or you're next to a benzene ring. So what that's saying is that if you can resonate, that's going to make the radical more stable than anything. And here I have drawn the allylic and the benzylic. This would be allylic. This would be benzylic. Okay? Notice that both of these are directly next to a double bond. So a double bond and the radical could switch places through resonance structure. And what that would do is that would delocalize that electron deficiency over several atoms, stabilizing it. Okay? So what I want you guys to be mindful of is that this is actually going to be important for reactions. These sites here are very, very crucial for reactions that we're going to learn later because they're very stable. Okay? So what I want you guys to do here is determine which of the following radicals would be the most stable by looking at this trend. Just basically looking, forget the carbocation one because we're not talking about those. We're just talking about radicals. Figure out which of these would be the most stable and why. Okay? Don't forget to look at resonance structures to make sure that you're looking at both of the ways that the radical could be represented. Because remember that in a resonance structure, they're constantly in hybrid of each other. Okay? So you can't just you can't determine stability just based on one of the resonance structures. Okay?